Hello, my name is Carly Hakla and I'm a sophomore. We have decided to collect baseline water quality data because of the close location of a proposed fracking site, only 1,500 feet from tributary T1. If fluids from the fracturing site were to enter this tributary, it would soon end up in our reservoir. In addition to T1 in the reservoir, we are monitoring 3 other tributaries to the reservoir: the Savage River aquifer, and the inflow and outflow of the Frostburg water treatment plant. By monitoring all 8 of these sites, every source of Frostburg's drinking water will have pre-fracking baseline data, even if no known threat currently exists. We are currently testing for 20 analytes as part of the baseline water study and are testing for all Tier 1 and Tier 2 analytes, except potassium. This table was presented at a meeting of the Maryland Water Monitoring Council that we attended in October to make sure that our procedure was in line with professional standards. We are also including the Tier 3 analytes of gross alpha and gross beta. An analyte is a particular substance that is identified in an analytical procedure. 2 of our most important analytes are barium and strontium. These 2 elements have a minimal presence in natural water, but are present in high concentrations in Marcellus Shale formation water. According to Dan Soder, barium is used in the drilling process as well as in the fracking fluid. Although it is difficult to tell whether barium in the water is from the shale or the drilling mud, it is a definite sign of fracking. A further very useful piece of data is specific conductivity, a measure of water's ability to conduct electricity as caused by the concentration of ions dissolved in it. Distilled water has 0 conductivity. Fresh natural stream water has fairly low conductivity. Fracking fluid has an extremely high conductivity due to many salts dissolved in it. Specific procedures must be followed to ensure that our data is collected in the correct way and so that our numbers can stand up to scrutiny. Prior to sampling, all instruments were carefully calibrated according to manufacturer standards. The field procedure for our water sampling sites is as follows. We will use the procedure at T1 as an example, though the identical procedure is repeated at every site. A tag line is installed before any work is done. Any stream walking is done downstream from the tag line. Sampling is done upstream from the tag line. pH is measured using a YSI pH 10 meter. This is done by placing the meter into the tributary and gently swirling it in the water. Once the number stabilizes, it is recorded on a data sheet. The next step involves the YSI Pro ODO, which measures the dissolved oxygen content of the water. The device is used by placing the sensor into the water at parallel to the surface. Next, a YSI Pro 30 is used and is operated in the same way as the Pro ODO. The Pro 30 displays specific conductivity in microsiemens per centimeter and water temperature in degrees Celsius. After data is retrieved, the turbidity or cloudiness of the water is measured using a Hack turbidimeter. Turbidity is measured in neoplometric turbidity units, or NTUs. Another student fills a total of 4 500 milliliter bottles. She or he fills 1 bottle up, caps it, inverts it, and then dumps the water out downstream. The student does 3 of these meter rinses for each bottle. On the 4th fill of the bottle, the individual reaches down and fills up together a depth integrated sample. These bottles are placed on ice. This exact process is repeated at each of the 4 tributaries that are tested. At the aquifer in the Frostburg Reservoir, the only change is that the water is pulled and tested from buckets, all of which have undergone 3 native rinses, because the water cannot be easily accessed otherwise. For the samples from the water treatment plant, treatment mix, and treatment raw, the water is drawn from faucets. The bottle samples from the streams are shipped on ice with a chain of custody form via FedEx overnight to Summit Labs in Cuyahoga Falls, Ohio, where they are acidified and refrigerated within 24 hours in order to meet the EPA standard. Once at the lab, all EPA guidelines for lab analysis are strictly followed, including analysis by inductively coupled plasma mass spectrometry and ion chromatography. The results are first emailed and, once verified, sent as a hard copy to Mountain Ridge High School, where the information is inputted into our baseline water quality Excel data files and then proofread independently 3 times. Additionally, at all sites except those of the water treatment plant, a HOBO continuous conductivity logger is removed from the water and inserted into a shuttle. This device records conductivity every hour around the clock. After insertion, the data from the previously submerged HOBO meter is downloaded to the portable shuttle memory storage device. The retrieved information is then brought back to the classroom, where it is transferred to the computer via USB port. The newly obtained data is then plotted on graphs in and outside. Analyzed. Now let's take a look at the data we have gathered and explain its significance for the systems of Frostburg.
This first graph is showing barium and strontium levels in tributary T1 from February 2012 to February 2013. The x-axis indicates the months the samples were collected. The y-axis is a measure of the depth of the stream in centimeters and also concentration in parts per billion. Parts per billion is an extremely small amount. As an example, 1 part per billion equals 1 white marble in 2,000 train cars filled with black marbles. Moving on to the legend, barium concentration is represented by the green line. Strontium concentration is represented with the red line. Lastly, the depth of the staff plate, a permanently installed metal meter stick-like measuring device, is represented by the blue line. Looking at the summer months on this graph, one can conclude that water levels drop drastically in the months May through September. This is because of the very hot, dry, drought-like conditions we experienced this past summer in western Maryland. Looking at the months of November through February, one can recall that the precipitation increased during these months, leading to increased stream depths. Next, it is important that the relationship between barium, strontium, and the stream depth is analyzed. When the water level is lower, the concentration of barium and strontium is increased. This can be described as an inverse relationship. Although in this specific graph, it appears that there is great diversity in our data between the months with the different peaks and valleys, it's imperative to note that all this data is within the natural variability of water, is measured in parts per billion, and that these changes are not the result of any human influence. The average barium concentration in tributary T1 is 33 parts per billion. The average strontium concentration is 42 parts per billion. On this next slide, you can see that we collected a similar data set at tributaries C6, B7, and G8. On the next slide, treatment raw, treatment mixed, the aquifer, and the Frostburg reservoir are also displayed. While there are some very interesting comparative differences from site to site, it is beyond the scope of today's presentation to fully describe them all. This slide is showing the specific conductivity of tributary T1 from June 2012 to February 2013, along with the depth of the water at the staff plate. The y-axis is in microsiemens per centimeter, and the x-axis is the month the water was sampled. Advancing to the legend, the yellow line represents specific conductivity, while the blue line represents the depth of the staff plate. Similar to the barium and strontium graphs, the graph with specific conductivity has an inverse relationship with the depth of the staff plate. The average is 132 microsiemens per centimeter. We have similar graphs for tributaries C6, B7, and G8. Here, we can also see the reservoir, aquifer, treatment mixed, and treatment raw. On the next graph, the 4 red lines from lightest to darkest measure calcium, chloride, sodium, and magnesium concentrations. The blue line, once again, represents the depth of the tributary of the staff plate. Similar to our other data, the chemicals and water depth have an inverse relationship. As the amount of water increases, the concentration of the chemicals decrease. Here is the similar data for the treatment mixed, treatment raw, aquifer, and the reservoir. The information is also available at our other sites. In all of the previous graphs you have just seen, multiple chemicals were measured at only one sampling site. On this graph, however, one chemical concentration, in this case chloride, at all 8 sites is being displayed. The chloride ion is relatively common in natural water. The y-axis measures concentration in parts per billion, while the x-axis displays sampling months. Of all the sites and dates combined, the average concentration of chloride is 43,000 parts per billion. You can see that the stream G8 stands above the rest, as it does for just about every other analyte. We hypothesized that its high values are due to the influence of a large cow and horse farm approximately 1 mile upstream. This next graph is where you will begin to see the importance of our data as a pre-fracking baseline, and you will begin to understand how useful our data is for the purpose of identifying potential contamination as a result of fracking fluid. When the exact same chloride data on the previous slide is graphed with the concentration of chloride in pure frac fluid, our peaks and valleys become insignificant and unnoticeable. As you can see, the scale of pure frac fluid is greater than 40 million parts per billion compared to chloride concentrations that you saw on the prior slide in natural water, which is averaged at 43,000 parts per billion. Therefore, frac fluid has a chloride concentration that is 930 times the natural level. Even when the frac fluid has been diluted to a mere 1/100th of its original concentration, as shown in this graph, the frac fluid chloride concentration is still significantly higher than any of our tributaries. Even at this dilution, it is still 9.3 times higher than our natural averages. This is a perfect testimony to the importance of our data. Even if a very small amount of frac fluid was released into our streams, we would immediately notice the contamination. This would be so, even for chloride, an ion that is somewhat common in nature. We would like to further emphasize this point by displaying similar data for strontium, an element that is relatively uncommon in natural water, but of a very high concentration in frac fluid. See this next figure. This graph displays strontium concentrations in parts per billion at all 8 sampling sites. Of all sites and dates combined, the average concentration of strontium is only 47 parts per billion. The next slide shows our strontium concentrations compared to that of pure frac fluid. The concentration of strontium in frac fluid is 1 million parts per billion compared to the strontium concentrations that you saw on the prior slide in natural water, which is averaged at 47 parts per billion. Therefore, frac fluid has a strontium concentration that is 20,000 times the natural level. Even at a dilution of 1 to 1,000, strontium levels are still 20 times higher than our natural strontium averages. It should be blatantly obvious if contamination occurs at any of our sampling sites. This table shows some other analytes we are monitoring for. The right-hand column shows the concentration of each analyte in frac fluid. As with every analyte mentioned thus far, our numbers are very minute compared to those in frac fluid. 2 fracking indicators to highlight: barium and strontium levels are each approximately 20,000 times higher than natural levels. Bromide may be our best indicator of all. Its levels in natural water have been below 10 parts per billion every month for every stream. Yet, in frac fluid, average bromide concentrations are 445,000 parts per billion. This next graph is different from all the others because this graph displays our continual data retrieved from our hobo conductivity loggers. These meters have been placed at 6 of our 8 sites and measure the conductivity of the sites every hour on the hour. This allows us to monitor our tributaries without having people in the field at all hours of the day. The red arrow is placed on the day of January 28, 2013. The massive spike in conductivity observed is the result of road salt rushing into the tributary when the snow first started to melt. The jump in temperature occurs 2 days later, giving the ice and snow enough time to completely melt before the water started to warm. The data on our hobo meters was somewhat similar in all of our tributaries. Again, the red arrow is indicative of the large conductivity spike. The final slide here shows what a contamination event might look like. We would expect to see a large spike in conductivity, perhaps increasing to 15 times more than the natural levels if diluted to 1 to 1,000. This highly diluted frac fluid still towers over even the most significant road salt runoff of this past season. The duration might be much longer than what is shown here. Hopefully, a contamination event like this is never observed, and citizens can continue to confidently drink from their water supply. After fracking begins, it is our hope to provide quarterly notifications indicating that the water is still safe to drink. However, if a spike of this type was noticed after fracking begins, we would immediately inform the Frostburg water treatment plant, the city government, and the public, and then proceed to take more detailed samples with our 20 other analytes to verify whether or not fracking was in fact the cause of the event, and to gain greater insight into the impacts of contamination. We would urge all who drink from the Frostburg supply to avoid drinking the water until the matter was resolved. At that point, we would request that a government agency would assist in further analysis, monitoring, and resolution of the issue. Hopefully, such contamination never occurs, and we will continue to report that our water is still safe.
Hello, my name is Jeffrey House and I'm a senior. There are 3 ways to access our data if you are interested in a more detailed analysis. First, you can email Mr. Kozakowski for a complete copy of our Excel file. Secondly, you can see some of our data displayed on the Maryland DNR website, where it is displayed alongside data gathered by our finest field scientists. Thirdly, you can go to www.shownetwork.org, a National Science Foundation-sponsored project to collect any data created by government agencies, university science, and community groups related to fracking and water quality, so that comparisons can be made. This requires a download of the Hydro desktop software. Furthermore, once our baseline data collection is completed in August of 2014, we hope to put it on file in the Frostburg Public Library and the Frostburg State University Library so that any concerned citizen can easily reference it. We also hope that you will check out our website linked to the State Farm Youth Advisory Board's project page. We sincerely appreciate your time and attention, and we would like you to go and like us on Facebook at Mountain Ridge Pre-Fracking Baseline. We kindly request that you post on our Facebook page with your comments, both positive and negative. If you prefer, you can also email the comments and questions to thomas.kozakowski@acps.k12.md.us. We welcome suggestions. All website and contact information just mentioned are listed on the handout that you received this afternoon. Please refer to it. Here's a list of all the students that have been involved with this project. It includes 136 individuals who have either gone into the field or helped analyze data, been involved in construction, research articles, or helped in some other way. Core leaders trained others in field data collection methods and were involved in several different aspects of this project. This final slide is a list of all the professionals that have given their time and support to this project. We are sincerely grateful for the many hours that have been spent assisting, teaching, organizing, proofreading, advising, and volunteering. This project would have not been possible without these efforts. It is our hope that you feel you have learned much about the pros, cons, and areas of uncertainty in policy developments related to hydraulic fracturing in Western Maryland. Most of all, we hope that when fracking does occur in our area, whether it be in 2 years, 5 years, 10 years, or more, you remember that our baseline data exists. We will be able to confidently inform you at that time whether or not our water is safe to drink. Thank you for your time, and we will now take more questions.
One more round of applause. I think okay, and we'll just have our panel stay up, and then we'll, others can take a seat for now, and we will continue with some more questions. Okay. Okay. Again, I just want to thank the students before we take questions for all of their hard work. They really have done an outstanding job. They've been diligent, persistent. They put in time, not just during the school day, but beyond the school day. Late at night, several times. We've had a group working to prepare for this. Saturday, they were here. Over spring break, they were here. Not here, at Mount Ridge High School. And they're just really, they've done a terrific job. I'm proud of all of them. So let's give them one more. Okay, let's go ahead with our questions. Yes, in the back.
If I heard correctly, there needs to do baseline water quality testing before drilling. did I hear that correctly, in Garrett and Allegheny County?
So I guess I'll just clarify that. Well, no, I'll let the student take a shot at it. So are they going to do baseline water sampling in Garrett and Allegheny County? As you heard, they are not. Can we answer that?
From the research that I've done, and if fracking would continue, Martin O'Malley has set aside some money for fracking tests, but this will only apply to drinking water resources that are within 2,000 feet from a fracking site. However, the Frostburg Reservoir is 3,200 feet, so it does not fall into this category.
Would that include landowners and individuals to do baseline quality testing?
I'll go ahead and clarify that a little bit more then. So the governor set aside $1.5 million for general environmental studies prior to even allowing fracking at all in our state, as I understand it. The 2,000 feet would be industry-funded baseline testing around specific fracking sites. Okay, so to get to the root of your question, baseline testing of some sort will be done in Garrett County. None will be done in Allegheny County. But within 2,000 feet of any fracking site, it will be done on all of those. If Eshleman and Elmore's recommendations are adopted by our state government, I know we have several government officials here, and that really lies in their hands.
Well, I'm Ann Bristow. I just want to mention this. I'm with the Savage River Watershed Association. I know you all have had some contact with us. We've actually been doing baseline monitoring in Garrett County for a year. We started in March of last year. So we have a year of data. The same DNR site that they put up, you can go to and see all the data. Both the Youghiogheny Watershed Associations and Savage River Watershed Associations are doing that baseline monitoring. Also, DNR is already, I guess MD is already doing monitoring of some selected wells in Garrett County. I think it's accurate to say that no baseline monitoring is happening in Allegheny County yet. This is stream monitoring I'm talking about that the two watershed associations are doing. But all that data is on the DNR website. You can look at it there.
So the only work within Allegheny County is our own, as far as I know. Other questions? And thank you, by the way, to the Savage River Watershed Association for the fine work you guys are doing. It takes a community and many people to really keep an eye on the industry and make sure they're doing their job right. And the more that people are watching, the more that I think they'll be careful. Other questions? It's in the back.
I think the baseline testing is very valuable that you're doing. The one side said that if they do find some kind of contaminants in the water, then you would somehow alert the citizens and we wouldn't drink it. I guess my question is, what will we drink, or what will we do? You know, how will we cook our food? What are we supposed to do? You know, water is what we need to live. So what's the plan for that?
Hopefully some government agency, the Maryland government, would step in and help us. We're probably going to have to rely on either boiling any water we have to use or using bottled water bought from stores that is safe to drink.
That's a good answer. More questions? Any others out there? Sydney.
I know that since I've worked on this, it's become a lot more, you guys have put a lot more into it. What has been the hardest part as a group of doing this project?
Well, since we've been doing this project this year, the focus has been on water testing, and that is, you have to be very detailed with it and follow a very strict process. So as we do that, we have a team here, and we all work together, and we've really taken on that. And as the project has grown over the past year, with the grant, that's what caused this large growth in the project. And we put the data into an Excel file. We have people who work on water sampling, and it's just, there's so many jobs that have to be put together, yet we all work together as a team to make sure that this project's completed and accurate for all of you.
Abby was out there in March, as well as Carly and Leah. Why don't you guys tell us a little bit about that day?
Well, it was about 10 degrees outside, very cold, and we were in very cold water. For, what, were we out there 5-6 hours maybe?
Yeah.
It involves hiking half a mile at the least to get to any of the places we want to sample. It's really, really time consuming too, that's the other thing, and we don't have unlimited time. I know for this year's AP Environmental Science class, we only have an hour and a half each day to do what we need to do, and it's really not enough time for us to do what we need to do.
Also, as being a member from last year's class, it was a lot time consuming putting the information together that we gathered only a few months when we first started, and trying to be able to put it together and get funding for this year, and we had to pull our information together, and then also this year as being some of the classmates from last year coming together to be leaders and trying to train the students from this year and other students to continue our research and to gather information and to do it accurately as we did.
No, I was there for the first year, and it was challenging getting it started to begin with, having to go through fine research about it when we first started, being able to pull everything together. We worked on it for, I think it was 4.5, 5 months that year, and there was 6 of us in the class, and we just shared all the work. We read through every article that was published that year on Marcellus Shale, and that's where everything started. We started as a class project writing letters to government officials, and it just started from there.
It's a great answer, Bryce. It's from class at about 16. Yeah, that's okay. Maybe one more good question out there. One more good question, and then we'll wrap it up. One more? Go ahead.
Just based on all the information that you have now, would each of you vote for fracking or vote against it?
Okay, I'll tell you what, that's the one question we decided before we started. And I'll tell you why. Well, I'll let the students tell you why, because they know why. Why aren't we going to answer that question?
If we give you our opinions, we don't want anyone to think that our data is in any way biased. We are trying to be as unbiased as possible, and if we told you what we thought, that wouldn't be good.
That pretty much covers it.
Have you discussed that in the class yourselves, and do you have like a common consensus, or no?
The class is quite divided on the issue, and there are a variety of opinions, some at every end of the spectrum and in the middle, and we'll say that. Okay. So thank you everybody for coming. I again want to have all the students stand up, including Dylan, and also we had Jessica and Kaya helping out, pass out flyers. That's everybody up to the front. Everybody up to the front. And Cindy, you've been part of this project, so come on up too. And let's give them one last round of applause. Thank you for coming.